Chemical engineering, like most of the branches of engineering we'll be studying over the course of the rest of the year, has a variety of different specializations within it. But for our purposes, we're going to be looking at the challenge for trying to unlock the potential energy of some sort of chemical compound and converting it into something useful for humans. And so the first step of this process is often combustion. So it's the reaction of a fuel with oxygen to generate heat, which then can be trapped and used to perform some sort of service or operation or drive some sort of mechanical outcome. Now, one specific type of process called distillation, which occurs at an oil refinery, the separating of various hydrocarbon fuels from a crude oil mixture. Before we get to that, we have to first review some of our basic chemistry and expand on that knowledge before we get to that. So from our chemistry days, recall that molecules are counted in large units called either gram moles, abbreviated with the MOL, or kilogram moles, so kilomoles, KMOL. And so a mole is the amount of substance containing as many elementary entities, atoms, molecules, etc., as are atoms in 12 grams of carbon-12. So that's the basis of that measurement called a mole. And so that number hopefully rings a bell for us here. So 6.022, etc., times 10 to the 23rd for a mole. Or if we're talking about a kilomole, we're just going to increase that by an extra factor of 1,000, so an extra times 10 to the third. Now, the atomic mass of an element is going to be measured relative to its mass of carbon-12. That's our foundation for all of our molar mass measurements. And so the relationship between the number of moles of a substance, the mass of a substance, and the molecular mass of a substance in either grams per mole or kilograms per kilomole is shown here. So we've got the number of moles is going to be equal to the mass of the substance divided by its molecular mass. If we think of that from a units perspective, the mass of the substance, let's say, is going to be in grams. The molecular mass then in the denominator would be in grams per mole. So in this circumstance, our grams would cancel each other out, and then the moles in the denominator of the denominator would move up into the numerator, which matches up with what our n variable should be. And so in our textbook, we've got a partial table of atomic masses that's located on page 107, so we can use that as a reference guide whenever we need an atomic mass for any type of calculation. So in this first example, we're asked to find how many kilomoles of carbon dioxide are found in a kilogram of carbon dioxide. We have the given atomic masses there at 12 grams or kilograms per mole and 16 kilograms or grams per mole or kilomole. So in our equation, n equals m divided by m. Remember, n is going to be the number of moles. M is going to be, the lowercase m is going to be the mass of substance that we have. So in this case, that's 1 kilogram of CO2. And then in the denominator, we need the molar mass of the CO2. So with a measures of carbon at 12 grams or kilograms per mole, kilomole, we'll stick with that. Oxygen at 16 kilograms per kilomole. So we've got 2 atoms of oxygen plus the 1 for carbon. Means we're going to have a molar mass of 44, and if we pay attention to our sig figs, we'll have 44.0 kilograms per kilomole. If my measurement up here was in grams, then I could have just used grams per mole, but I'm going to try to make it simple on myself for simplifying. And so we just have to divide those two quantities. We're going to get 0.0227 if we push buttons on our calculator, 1 divided by 44. And then again, our kilograms cancel each other out. Kilomoles is in the bottom of the bottom, so it's going to move up to the numerator. So it's going to be kilomoles of CO2. In the second example, now we're trying to find the mass in grams of 5 moles of water. So we can again use our same equation. Number of moles is equal to the mass of the substance divided by the molar mass of the substance. So this time we know what N is, so that's our 5 moles. So my mass of the substance is what I'm solving for, which means I need to know what the molar mass of the substance. So in the case of water, H2O, that means we have 2 atoms of water at 1.00 grams per mole, plus our oxygen from up above at 16, so we've got 18 grams per mole of water. And so now to solve for M, we can just multiply both sides by 18 grams per mole. Hopefully we can see that those moles units are going to cancel each other out. And so we just end up with 90 grams of water in this case. Now in the last question here, we're asked to find the effective molar mass of air. Now, of course we know that there is no air molecule, but it is a necessity for us in some of our work down the road to have an estimate of what the effective molar mass of air is. And so if we consider that air is almost exclusively composed of 79% nitrogen and 21% oxygen, with just trace amounts of everything else, we can come up with a reasonable estimate of the molar mass of air. And so the way we can do that is to just take the 79% that is nitrogen, so take 0.79 and multiply that times the molar mass of nitrogen. So nitrogen has a molar mass of 14 grams per mole. So since it exists as N2, we need 2 atoms of it. So we've got 28 grams per mole. And then we're going to add to that the 21% of oxygen. So oxygen, again, from our previous slide, 16 grams per 1 atom. Since oxygen exists as O2, we're going to multiply this times 32 grams per mole. Try that again. And so what we end up with then through this calculation is an estimate of 28.8 grams per mole as the effective molar mass of air. Because so often when we're trying to combust something, we're not burning it in pure oxygen, we're going to be burning it in air. And so in our calculations, we're going to need to use this effective molar mass of air from time to time. So we'll expand on this idea more when we get deeper into the chapter, but I want to make sure that we were introduced to this concept of an effective molar mass for air so that we have a point of reference for later.